In this video we'll look at acetic acid vibrations and ferrocene MOs. Start Uscal and start Moilin, and in build mode click the screen. The default atom type is carbon. If we select a carbon with 3 connections, an sp2 carbon, click one of the hydrogens, click the sp3, and we have a methyl group added. If we click one of the hydrogens and change the atom type to O, case doesn't matter, we add a single bonded O, we add a bent OH, and we have completed acetic acid. Now to calculate acetic acid's vibrations, we go to Orca, New Input, and we select Calculate Spectrum, and then we click Run. So Orca is now running. Well, it's not yet running. Do you really want to run Orca? Yes. Orca is running and it's finished now. It takes a while, but we've shortened it here. Geometry converged is good. We look at the properties, and first thing we plot the IR spectrum, and we can see that it's calculated the OH vibration where we expect it and the C double bond O vibration. Now we can animate the vibrations by going to Properties, Animate IR, and if we go to the highest frequency, 1, and click OK, we see the OH stretch. And if we look for the one around 1900, which is where it has calculated the C double bond O, we see that animates. So it's easy enough to do this. Now you can also, when you've completed an Orca calculation, always use multi-wave function to have a quick look at the molecular orbitals. And we'll just briefly look at them here. When you start multi-wave function, 0 return starts a view of the orbitals. Now this is a very simple display, but it's very powerful. HOMO orbital is 16. So if we look at the HOMO and the HOMO minus 1, so if we go to 16, this is a lone pair orbital, and if we go to 15, we see that it's the C double bond O orbital. Now it's much better to look at Ferrocene to see how to look at orbitals in detail. So the first thing we'll do is we'll use Moilin to build Ferrocene. So build mode again, click the screen and type Fe for the atom type, and pick a 2 coordinate iron with 2 bonds, click one of the hydrogens and add an afa2 cyclopentadienyl ring. Do the same for the other hydrogen, and we see we have ferrocene generated. Now if we rotate this a bit, we can see we have 2 centroids. We need to remove those. If we go to remove and remove centroid, we can now do an Orca calculation on ferrocene. So we go to Orca, New Input, and just click Run. And again the program will say, do you really want to run Orca? And you say yes. So Orca is running now. And when Orca has finished, we can look at the orbitals using multi-wave function. Now again, 0 will show the molecular orbitals. Now in this case, there are a lot more orbitals in the case of acetic acid. The HOMO is now orbital number 48. So if we go to 48 and look downwards, we might see orbitals we recognize as being significant. So we move down to orbital number 48, where the HOMO is. If you can use up and down to rotate the molecule. We see this is not significant. There isn't strong bonding between iron and the ring in that case, nor in 47. If we go further down, 48, that looks like the iron dz squared orbital, which is non-bonding in ferrocene. And below that, 45 and 44 are the main bonding orbitals in ferrocene. We can see they're orthogonal. We'll see this in more detail now in a moment. Now, if we return, and if you press Q, lowercase q, return, you gracefully exit multi-wave function. And if we run multi-wave function again, we now know we want orbitals 44, 45, 46 plotted. We're now getting the multi-wave function program to write cube files of electron density for these three orbitals. That's done. We can now use the program Chimera to draw these orbitals. So just type Chimera if you have it installed. It should come up. And in Chimera, if we go to File, Open, it's already pointing at the Ferrocene folder where the Ferrocene calculations were done. Now the first thing you must do is open the Orca PDB file. This is written by Orca when Uskal is driving it. So you can see this has given us the molecule. Now we add the orbitals to this by just opening the maps that we have generated. The cube files are the maps, and 44 is the first one. So if we open that, we see it comes up with two level bars, one on the left and one on the right. Notice the level bar and the color button are the same color. If we click the color button, we can change, for example, if we make the left bar red, we make the orbital as negative red, and the one that's on the right, if we make that blue. So we have now got red and blue, and if we go to Action Surface, Transparency, and set that to 30%, it's reasonable level of transparency. Now if we move down the color picker, and if we now open another map, this time we open the one that's orthogonal to that one, as we saw earlier. See, it's at right angles to that one, to the first one, and we can set the colors on this one the same way as we did. We set the one on the left to be red, and the one on the right, the level bar on the right, to be blue. Then we have the same color scheme as we had already. Now, you don't of course always want to have all the orbitals displayed together, but you can select any of them and remove it. You can put it back by just clicking it again. Now we can again set the surface of the one we've just loaded to 30%. So these two are orthogonal, as we saw, 44 and 45. They're at right angles to each other. This means that if you rotate one of the rings relative to the other, you break one of these bonds and make the other. This effectively makes the barrier's rotation very small, because it's concerted bonding as you rotate around. Now, if we open the map for 46, we can see it's the dz squared, which we had, but we need to change the level bar slightly. You should move both of them the same amount away from the origin. And we have the dz squared, and we can color this to be the same color scheme as the previous two. Left on the red and blue on the right. And again set the transparency to be the same as the others, 30%. So the dz squared orbital is non-bonding. It's not pointing at the carbon atoms, it's pointing to the center of the ring, and so there's no effective orbital overlap. Now we can get a picture of these orbitals once we've generated them by simply asking the system to save the file. If we do File, Save Image, and PNG is selected, if we type in the orbital number for this one, MO44, then we will get a PNG file of orbital number 44. In this way you can produce high quality plots rapidly using the combination of USCL, Orca and multi-wave function.